If you are managing a Kubernetes cluster right now by, manually copy pasting YAML files from various dark corners of the internet, you're essentially building a house of cards on top of a fault line.
Oh, absolutely. It's a disaster waiting to happen.
Right. I mean, think about it. You've got your core application running, you've got your networking rules set up, your configuration data mapped out, permissions. It's all tightly wound together.
Yeah, it gets incredibly complex, incredibly fast.
Exactly. Basically, you've created this massive tangled web of YAML text files just to get, like, a single web server off the ground. And miraculously, it actually works.
For now, anyway.
Yeah, right, for now.
Yeah.
Because then, inevitably, you need to update it, to a new version, or maybe you just need to change the resource limits. And one tiny mistake in updating that tangled web, like one misaligned indentation, and the whole thing just comes crashing down. Utter panic.
It really is. I mean, it's the moment literally every systems engineer dreads. You're basically being asked to swap out the bottom row of that house of cards while the wind is blowing.
Which is terrifying.
It is, because trying to keep track of how all those interdependent files relate to one another over time and, in what specific order they actually need to be updated is practically impossible for a human being to do reliably at scale.
And eliminating that sheer panic is exactly why we are here today. So welcome to the deep dive. Our mission today is to completely conquer Helm, which is the de facto package manager for Kubernetes.
Which is a huge topic, but so important.
It really is. And we are pulling from some incredibly solid sources for this. We've got the official KCNA exam curriculum, the official Helm documentation, and we're also going into the depths of Artifact Hub.
Yeah.
We're basically going to figure out how we move from that chaotic, terrifying YAML copy-paste nightmare to a clean, predictable, and, reliable system.
Yeah, and that transition is just a fundamental milestone for anyone working with Kubernetes because, deploying a real production-ready application, it almost never involves just one file.
Right. It's usually a lot more.
Exactly. A standard application might require 10, 20, or sometimes dozens of different Kubernetes resource definitions. And when you start managing multiple applications across different environments like development, staging, production, doing all of that manually is just a guaranteed path to failure.
Yeah, I've been trying to visualize this shift, in how we manage the infrastructure. And it feels to me a lot like building furniture.
Oh, I like that. How so?
Well, using raw Kubernetes YAML, like just running kubectl apply on a directory full of files, is kind of like trying to build a complex piece of furniture from raw lumber.
Okay, yeah.
Like someone just drops a pile of wood, a saw, and some nails in your living room.
Okay.
There are zero instructions. You have to measure, cut, assemble everything completely from scratch, and you're just hoping it functions like a chair when you're done.
And if you make a mistake cutting the wood, you can't really uncut it. You basically have to go find more lumber and start over.
Exactly. It's unforgiving. But Helm, on the other hand, acts like flat pack furniture.
Right, like the IKEA approach.
Yeah, exactly. It's the box you pick up from the store where everything is already pre-cut for you. It's all in one package. It comes with a standardized instruction manual, and all you have to do is supply the specific dimensions or colors or hardware you want for your space. You don't need the saw anymore. You just need the little hex wrench it comes with.
I mean, the mechanics of that metaphor actually map quite closely to the technology. Helm essentially takes all of those disparate YAML files, so your networking, your storage, your workloads, and it bundles them into a single cohesive unit.
So it's doing the heavy lifting.
Exactly.
Yeah.
You aren't rewriting the core logic of how the application works. You are just passing in the specific variables your specific cluster environment needs.
Right. Okay, I do want to play devil's advocate for a second, though.
Sure, go for it.
If I am just spinning up a tiny, simple project, maybe just a single pod to test a script, is going through the trouble of installing and learning a whole new package manager just overkill? Like, why not just stick to the raw lumber and use Codex Solo, apply for the small stuff?
Well, to be fair, raw kubectl apply absolutely still has its place.
Okay.
Yeah, for very simple, localized testing or single-file deployments, it's fine. I mean, you don't need a factory assembly line to build a wooden block, right?
Yes, that makes sense.
But Helm's true value unlocks the literal second you introduce any kind of complexity or longevity. Think about the life cycle of an application. If you use kubectl apply to update those 30 raw files we talked about, and something breaks, how do you realistically undo it?
Oh, man. I guess I would have to manually figure out exactly which of those 30 files changed, what the previous state was before my update, and then manually reapply the old code.
Right.
Which, if the site is actively down and people are yelling at me, is a terrifying prospect.
It's extremely dangerous and highly error-prone, but because Helm manages the application as a single package release, it keeps a hidden history of what it has deployed.
Wait, really? Like
Yeah.
a built-in history?
Yeah. So if an update crashes your app, Helm has a built-in rollback command. You can revert the entire application, all 30 of those underlying resources, back to the exact previous working state instantly.
Oh, wow. Just instantly.
Instantly. That safety net, the ability to treat a complex distributed system as a single version entity, is basically why you want Helm managing your production apps.
Okay, that is huge. So if we want to effectively build this flat pack furniture and, actually use that safety net, we first need to understand exactly what is in the box and what to call the pieces.
Absolutely. Terminology is key here.
Right. So looking at the KCNA curriculum, there are 4 essential concepts you need to know: the chart, the release, the repository, and the values. Let's start with the chart. That's basically the flat pack box sitting on the shelf, right?
Yes, that's the package itself. The chart is the bundle of files and templates necessary to create an instance of a Kubernetes application. It defines what the application looks like, but crucially, it is not running code. A chart on its own doesn't actually do anything in your cluster. It's just the definition.
Got it. So to make it actually run and do something, I have to install it, which then creates the release.
Exactly. A release is a running, deployed instance of a chart in your Kubernetes cluster. And the defining characteristic here, and this is important, is that one single chart can generate many, many different releases.
Wait, so I could download a single web server chart, like one box from the store, and install it 3 different times, like to create a development release, a staging release, and a production release.
You absolutely can.
And they just run simultaneously side by side in my cluster.
Yep. And each of those releases will operate completely independently, tracked by Helm under different release names.
That's incredibly efficient.
It really is.
Yeah.
Now, you mentioned downloading that chart earlier. That happens via a repository?
The repository.
Right. A repository is simply an HTTP server that houses an index file and packaged charts. It's basically the warehouse where all these flat pack boxes are stored and versioned.
Okay, so we've got the chart, the release, the repository. And the final piece of the puzzle is the values. So if the chart is the generic flat pack box, the values are the custom dimensions we supply.
Spot on. They are the configuration parameters. Values are the specific settings like, say, which port to open or exactly how much memory to allocate that you inject into the chart when you create a release.
Oh, I see.
Yeah, this allows you to customize the deployment completely without ever having to touch or alter the original chart files.
Let's actually unpack that box, because I know the KCNA exam expects you to know what it looks like inside. If we open the internal directory structure of a Helm chart, there's a very specific anatomy, right?
Yes, very specific.
Right. We have the chart.yaml file, which is essentially the metadata label on the outside of the box. It holds the name, the version number, the description of the chart, and then you have the values.yaml file, which hold all those default configuration parameters.
Right, and then beneath that, you have the real engine of the chart, which is the templates directory. This is where all those raw Kubernetes YAML files live, but they look a little different.
Different how?
They are written using a templating language, specifically Go templates.
Ah, okay. Let's extend our metaphor here, because I feel like this is where the magic actually happens. The values.yaml file is essentially your custom order form, right?
Yes.
And those Go templates inside the directory, they're the factory machines that read your order form and literally cut the wood to size before shipping it out to the cluster.
That's a really great way to visualize it, because instead of hard-coding a port number like 8080 into the deployment file, the template will have a placeholder.
Like a variable.
Exactly. Something that looks like double curly braces surrounding .values.service.port.
Oh, okay. I've seen that syntax.
Yeah. So when you install the chart, Helm's rendering engine takes your custom order form, finds that placeholder in the template, injects the actual number 8080, generates standard raw Kubernetes YAML, and then sends that finalized YAML to the Kubernetes API.
I want to pause here for a second and offer some reassurance to you, the listener, especially if you are actively studying for the KCNA exam right now.
Yeah, it can sound like a lot.
It really can.
Yeah.
Hearing about rendering engines and Go templating syntax can sound incredibly intimidating, but there's a very clear boundary for the exam. You only need to understand this structure mechanically.
Right. Don't panic about writing code.
Exactly. You just need to know that chart.yaml holds metadata and that templates use values to generate manifests. You are definitely not expected to actually write complex Go templates from scratch or build a totally custom chart yourself.
No, not at all. The exam mainly tests your ability to operate Helm, to be a competent user of the package manager, not necessarily to be an advanced software developer authoring charts from the ground up.
Okay, good. So we understand how the order form feeds the factory machines.
Yeah.
But what if I just don't like the defaults? Like, I have this default values.yaml file that comes baked into the chart. But I don't want to edit that original file directly because then I break the reusability of the chart for the future. So how do I inject my custom configurations safely?
Well, Helm solves this with a very strict hierarchy of configuration. It's actually designed specifically so you never have to touch the original files.
Oh, nice.
Yeah. At the very bottom of the hierarchy, with the lowest priority, are those chart defaults, the settings written into the values.yaml file inside the chart itself, basically the factory settings.
Right. But I can override those factory settings by creating my own separate custom values.yaml file on my laptop and just passing it to Helm when I run the install command.
Exactly. Helm will process your custom file, and if it sees a value that contradicts a default, say the default replica count is 1, but your custom file says 3, your custom value wins.
Awesome. But it goes one step further, right? What if I just want to change one tiny thing on the fly, like maybe updating an image tag during a quick test, and I really don't want to bother writing and saving a whole custom YAML file just for that one thing?
That brings us to the absolute top of the hierarchy, the command line flags.
Okay.
You can use the set flag directly in your installation commands, so you might just type set replica count 5.
That beats everything else.
It does. The flow of precedence is this. Chart defaults are overridden by a custom values.yaml file, which is in turn overridden by any set flags on the command line. The command line always has the final say.
That gives you incredible flexibility. Okay, so now I have this concept of a flat pack box, but I don't want to build my own Nginx or Redis box from scratch.
Yeah.
Where's the IKEA in this scenario? Like, where do I go to actually pull these down?
You go to Artifact Hub. Artifact Hub is the central public repository aggregator for finding, installing, and publishing Kubernetes packages. It's essentially the global catalog where the open source community and even enterprise software vendors share all their Helm charts.
Okay, but this raises a massive red flag for me regarding operational security.
Oh, definitely. You have to be careful.
Right. Because if I am downloading a package that is going to configure the core infrastructure and networking of my production environment, how do I know what to actually trust? Anyone can upload to a massive public hub. If I just grab, like, the first search result for a database chart, I could accidentally download a package that has misconfigured security settings. Or worse, someone could have hidden a crypto mining sidecar container inside the templates.
You've hit on a really critical operational risk there. You absolutely cannot blindly trust public packages.
So what's the solution?
When you are evaluating charts on Artifact Hub, you have to look for the verified publisher badge.
The verified publisher. Got it.
Yeah, Artifact Hub has a verification system that essentially proves a chart is officially maintained by the organization that actually owns the underlying software. So if you need an Nginx chart, you look for the one verified by F5 Nginx, not just some generic community chart uploaded by a user with, a pseudonymous handle.
Right, that makes total sense.
Prioritizing verified publishers is just the baseline for ensuring security and reliability in your deployments.
All right, so we found our verified chart. We understand our configuration hierarchy. Let's trace the actual lifecycle of our deployment. We need the operator's manual now. Let's walk through the exact workflow, step by step, using the core commands tested on the KCNA.
Okay, let's do it. The lifecycle actually begins before you even install anything with the command Helm repo add.
Why do we start there?
Because your local Helm client doesn't automatically know where every chart lives. You have to explicitly tell it to connect to a remote repository, providing the URL so it can download the index of available charts from that specific warehouse.
Okay, so once my client knows where the warehouse is, then I type Helm install.
Yeah.
And this is where the magic happens. But what's actually occurring between my terminal and the Kubernetes API when I hit enter?
Good question. When you run Helm install, Helm reaches out to that repository, pulls down the chart, takes your custom values from either your file or your set flags, and feeds them all into the rendering engine.
Right, the factor machines.
Exactly. It generates all the raw Kubernetes YAML locally in memory, and then sends those completed manifests to the Kubernetes API server to create the resources.
And it tracks it, right?
Yes. It creates a secret in the cluster to record exactly what it just did, marking it as revision 1 of your new release.
Now the application is running. A week goes by, and my team lead says, we need to see what's actually operating in the cluster right now. I'd use Helm list, right?
Yep, Helm list simply queries the cluster for all those hidden tracking secrets Helm created. It displays a really neat table showing you the names of all currently deployed releases, what namespace they're in, their current status, and what revision number they're currently on.
Okay, so I check the list, I see my release, but we realize we need to update the application to a newer version. Why do I use Helm upgrade instead of just running Helm install again?
Well, if you run Helm install with the same release name, Helm will actually throw an error because that name is already taken.
Okay.
Helm upgrade tells Helm to take an existing release and either apply a new version of the chart or just apply new configuration values to the current chart. Helm then calculates the differences and smoothly transitions the running application to the new state, and that creates revision 2.
And if that upgrade goes horribly wrong, we hit the safety net we discussed earlier, Helm rollback.
Exactly. Helm rollback tells Helm to look at its internal history, find the exact manifests it used for revision 1, and immediately apply them to the cluster, reverting the application back to its previously stable state.
Finally, the project is over, and we need to clean up. So Helm uninstall completely removes the release from the cluster, deleting the associated Kubernetes deployments and services.
Right, it's a clean sweep of the application footprint.
Okay, I want to zoom in on something you mentioned during Helm upgrade. You said Helm calculates the differences. I was reading about this, and the mechanism it uses is called the three-way merge. And this seems to be like a massive conceptual leap from how basic YAML application works.
It really is. It is the defining feature of Helm's upgrade intelligence. To understand why it's necessary, think about a lesser system. A basic deployment tool might just look at the new chart you want to deploy, compare it to the old chart you deployed last week, calculate the difference, and push it. That's a two-way merge.
But a two-way merge ignores reality, right? I mean, it assumes nothing's happened in the cluster since last week. Like, what if an administrator had to jump onto the cluster at 3 a.m. and manually typed kubectl scale deployment to increase the replicas from 2 to 5 because of a massive traffic spike?
That is the exact scenario where a two-way merge fails catastrophically. If Helm only looked at its own history, it would see that the old chart said 2 replicas, your new chart says 2 replicas, and it would blindly crush the administrator's manual intervention. It would just scale the application back down to 2 in the middle of a traffic spike.
Oh, wow. That would be a disaster.
Yeah.
So how does a three-way merge solve that?
Helm looks at 3 distinct states. First, the old chart it originally deployed. Second, the live current state of the cluster running right now. And third, the new chart you are trying to deploy.
It compares all 3.
Yes. It sees that the original state was 2 replicas, but the live state is 5. It recognizes that a manual change occurred outside of Helm's purview. So when it calculates the diff to apply the new chart, it respects that manual change, ensuring that critical interventions aren't disastrously overridden without warning.
That is incredibly smart engineering. It tracks what it intended to do, what actually happened in reality since then, and what you want to do next. Okay, let's take all of this theory and bring it directly into some KCNA exam traps and, real-world scenarios.
Let's do it.
I was looking through the curriculum, and there's one specific trap regarding Helm uninstall that I guarantee trips people up. Let's say you've got a database running via Helm. If I run Helm uninstall, it completely wipes out every single Kubernetes resource created by the chart.
That is a very dangerous assumption, and it is completely false by default.
Okay, explain that.
While Helm uninstall will diligently remove your deployments, your services, your config maps, your networking rules, it intentionally does not delete persistent volume claims or PVCs.
And for context, a persistent volume claim is the resource that actually holds the storage, right? Like the hard drive space where your application writes its data.
Exactly. Think about that database scenario. If you uninstall a database chart, perhaps because you just want to migrate to a slightly different architectural setup, you absolutely do not want the package manager to automatically delete the hard drive containing all of your customer records.
Yeah, that would be a career-ending move.
Pretty much. So Helm is designed defensively to protect your data. The PVCs persist in the cluster after an uninstall. You have to manually target and delete them with kubectl if you really, truly want the data gone.
That is a brilliant design choice. Okay, let's puzzle through another common scenario you might see on the exam, or even just in a staging environment. Let's say you are trying to update a worker node parameter. You go into your custom values.yaml file, you change the worker count from 2 to 4, and you save the file. You run Helm upgrade, the command succeeds, but when you check the cluster, it's still running exactly 2 workers. The parameter just isn't taking effect. What went wrong?
Well, when a value in your file is ignored, it is almost always a test of your understanding of the configuration hierarchy.
The hierarchy we talked about earlier.
Right. If you know the file is correct, you have to check if a higher priority method is overriding it. You would need to look at your deployment scripts or your CI/CD pipeline logs and see if a set flag was accidentally left on the command line during the upgrade command.
Oh, because the command line wins.
Exactly. Because the command line is the absolute top of the hierarchy, a set worker count 2 flag will silently override whatever you wrote in the custom values.yaml file every single time.
That's sneaky, but makes sense. Let's do one more scenario. It's late on a Friday afternoon. A junior engineer is tasked with cleaning up a cluttered staging namespace, but they get their terminal windows confused and accidentally run Helm uninstall on your primary analytics database in the production cluster.
Oh no!
Yeah. The release is totally gone. The pods are terminating. They are hyperventilating. What is the path forward?
Okay, well, this relies exactly on the trap we discussed earlier. You tell them to take a deep breath because you understand how Helm handles data. You rely on the fact that while the database engine itself, like the pods and the networking services, was deleted, the actual analytics data is safe.
Because the persistent volume claims persisted.
Exactly. The solution is actually relatively straightforward. You simply reinstall the Helm chart, making sure the configuration points back to those exact same surviving PVCs. The new pods will spin up, attached to the old hard drives, and the database will just come right back to life with the data intact.
Crisis completely averted. So what does this all mean for you, the listener? Let's trace our journey today. We started with the sheer terror of raw, unorganized YAML files. 30 separate documents that you had to manually shepherd, update, and fix inside a cluster like a fragile house of cards.
Which nobody wants to do.
Right. And we've moved to the structured, predictable elegance of Helm. We now utilize charts, which are our flat pack boxes. We deploy releases, which is the functional furniture in our cluster. We use repositories to source them safely, and values to customize them completely without breaking the original blueprints.
And we understand the underlying mechanics of how it operates so safely. We know the hierarchy of values that gives us all that flexibility. We understand the brilliance of the three-way merge that prevents us from accidentally crushing manual cluster interventions. And, of course, we know about the protective safety nets like the instant rollback command and the fact that persistent volume claims survive uninstallation to protect our data.
Mastering Helm isn't just about ticking a box to pass the KCNA exam. It is quite literally the shortcut to maintaining your sanity as an engineer. It is how you manage deeply complex distributed applications without losing track of your infrastructure, and it's how you protect your organization's uptime when things inevitably go wrong.
Helm beautifully abstracts away the overwhelming complexity of Kubernetes, allowing you to operate at a much higher, more strategic level. But it does leave us with a final thought to ponder as you continue your journey.
Oh, what's that?
Well, Helm hides all that raw YAML so effectively and makes the system so easy to manage that it arguably creates a new kind of risk.
Interesting.
Yeah, does relying so heavily on a package manager risk, making us forget how the underlying Kubernetes resources actually connect. Think about it. If you only ever build flat pack furniture, and one day the system breaks down and the box arrives without the instruction manual, do you still know how to work with the raw lumber?
That is a great question to leave you with, and definitely something to keep in mind as you study. Until next time, keep exploring.